In this video, we are going to give a closer look on elasticity of substitution, what it has to do with families of CES production function, and the derivation of Cobb-Douglas production function. Elasticity of substitution can be defined as a ratio of proportionate change in capital labor ratio to proportionate change in marginal rate of technical substitution of labor for capital. Imagine an isoquant on a 2D plane. The capital labor ratio of any point on an isoquant can be represented by the angle produced with horizontal axis of an arrow passing through that point and the origin. Any point on a particular arrow will represent the same capital labor ratio. For instance, point A, B and C have the same capital labor ratio, and point A1, B1 and C1 have the same capital labor ratio too. Now suppose our initial point is A0 and we move to point A1 along Y1 isoquant. On this move, proportionate change in capital labor ratio can be viewed as angle 1 minus angle 0 over angle 0. In this scenario, MRTS LK shows how much quantities of capital input a producer has to give up for one additional unit of labor input so that his output remains intact. Under limiting case, it is just the slope of an isoquant at an instant point. Now take a new isoquant having less curvature than original isoquant Y1. Suppose our initial point is B0 and we move to B1 along new isoquant. Point B0 and A0 have the same marginal rate of technical substitution of labor for capital and capital labor ratio, whereas point B1 and A1 have the same marginal rate of technical substitution of labor for capital only. The proportionate change in slope from moving point B0 to B1 is the same as the movement from A0 to A1, but the proportionate change in capital labor ratio from moving point B0 to B1 along new isoquant is greater than from moving point A0 to A1 along the original isoquant Y1. The proportionate change in capital labor ratio from moving point A0 to A1 along original isoquant Y1 can be shown as angle 1 minus angle 0 over angle 0, whereas the proportionate change in capital labor ratio from moving point B0 to B1 can be shown as angle 2 minus angle 0 over angle 0. Since angle 2 is less than angle 1, therefore in absolute term we can say the proportionate change in capital labor ratio from moving point A0 to A1 along the original isoquant is less than the proportionate change in capital labor ratio from moving point B0 to B1 along new isoquant. Now the denominator are same in both the cases, but since proportionate change in capital labor ratio in case of initial isoquant having comparatively more curvature is less than the proportionate change in capital labor ratio in case of new isoquant having comparatively less curvature. Therefore, the elasticity of substitution of initial isoquant Y1 will be less as compared to the new isoquant. Therefore, in general, we can say more the curvature an isoquant have, less the elasticity of substitution it will have, and vice versa. Now we are going to derive the Cobb-Douglas production function. In the previous video we derived this equation and we solve for CES production function. Now if we take elasticity of substitution as 1, then 1 over sigma becomes 1. Now replacing 1 over sigma by 1, rearranging the position of del L and del K. Now let's take integral on both sides, which is equal to alpha times log of L is equal to negative of 1 minus alpha times log of K plus log of h of y. The arbitrary constant of partial differential equation in general can involve any function of variable or variable held constant. We have denoted that constant of integration as log of h of y, since we determined the slope of isoquant holding output, that is y, as constant. Taking anti-logarithm and rearranging, we get L to the power alpha is equal to h of y over k to the power 1 minus alpha, which is equal to h of y is equal to L to the power alpha times k to the power 1 minus alpha, or y is equal to f of L to the power alpha times k to the power 1 minus alpha, where f is the inverse function of h. Since our production function is homothetic by assumption, indeed h of y is monotonic. If we insist this production function to be homogeneous of degree 1, then it will take the form y is equal to a times L to the power alpha times k to the power 1 minus alpha. This is the form of Cobb-Douglas production function. Now we are going to discuss the relationship between CES production function and Cobb-Douglas production function. CES production function are those production functions which have a fixed elasticity of substitution in their entire range. In other words, any instant point of this curve has the same elasticity of substitution. But what will be the value of that fixed elasticity of substitution? In case of CES production function, it may take any value, but if it is 1, then its associated production function will be the Cobb-Douglas production function. In other words, the Cobb-Douglas production function are a special case of CES production function. Now I am going to show you some interesting graphical visualization of CES production function. E here represent elasticity of substitution and R here represent the parameter rho in our elasticity of substitution production function. This is our CES production function. We took output as 2 unit and A here represent overall factor productivity. We took share of labor as 0.5 and share of capital as 0.5 as well. X here represent labor and Y here represent capital. Now let's see how this parameter affects the graph of our CES production function. Now as you can see, if I increase the value of R, the curvature increases and vice versa. If the value of R approaches towards infinity, the elasticity will approach towards 0. The graph of our CES production function will something look like Leon-tip type isoquant. Now let's see how the parameter A affect the graph. Okay, if I increase the value of A, the graph shifts towards the origin. This is because to produce same level of output, that is 2 unit, we now require less and less factor input, or we now require lesser capital and labor. And if I decrease the value of A, then the graph move away from the origin. This is because now to produce same level of output 2, we require more and more factor of production. This is sometimes called the technological coefficient.